when people actually start using this chip, it turns out they need to do somewhat different processing than I thought because the standards changed or I didn't entirely understand what people were going to do with it. If that's not enough flexibility, then they just can't use it. Okay, so this could be faster and cheaper. But it's not very flexible. And not very flexible kind of means risky. Now, if you're deciding to put this in hardware, you have to be pretty sure that you understand what the end users are going to do with it. And if you get it wrong, then they're not going to buy your chip. Okay, so that's an advantage of an FPGA over an ASIC. In an FPGA, if you got it wrong, you can still change it. You can reprogram the design. So you can kind of take a few more risks about maybe being a little more limited in what your streaming units can do, how they're connected, because you can still change it if you got it wrong. If you made a custom chip, you can't change it. So you're going to tend to make it overly flexible. Okay, so let's talk about, so we talked about FPGAs versus ASICs, or versus processors. Let's talk about them a bit versus ASICs. Because I said that's basically what a modern ASIC looks like. It's also basically what most modern FPGA designs look like. Yeah? Which one? Here? Oh, okay. So I guess basically what I put up here is like, let's say I want to make something that's not a processor. Okay? Because if you're just making like a processor, you got to ask yourself, why are you doing that? There better be some uniqueness. If you're going to make a processor and compete with ARM and Intel and AMD, that's probably suicide, right? So that's not a good idea. So if you're making a chip, you have to think, well, what am I doing? I'm going after something different. So I'm saying here, okay, I know something about my application domain. So I know, because I came from the FPGA industry, I know a lot of it is about wireless processing. So let's say I'm looking at the next generation wireless standard, and I'm looking at what communication protocols are in it. I'm not actually 100% sure yet because it's not locked down, and there are these huge debates where all these companies are jockeying for advantage, trying to get their standard to reflect what they're working on. So I might put multiple units in because I'm not quite sure what my cell phone or my base station is going to talk to, okay? But I've got to put some hardware units in. I know streaming's really efficient for things like signal processing, so I'm not going to just do it on a processor because then I'm not going to be efficient enough, okay? I'll take a shot at a few different streaming units that I think I need, and then I know I'm going to need some control processing, and I also might have forgotten bits. Like parts of the standard might change, or I might have missed some stuff. So I put a microprocessor in. That's what a typical ASIC looks like, or a typical FPGA design looks like if you're talking about a big design. Does that make sense? So it doesn't really build like just all streaming hardware that does one thing, because it's a bit too risky. It's a bit too specific. So it usually is this mixed kind of thing. But it also isn't just one giant microprocessor unless you're Intel or AMD or ARM, right? Because that's what they do, right? They will go spend $10 billion making the best microprocessor they can, and they'll sell a lot of them. If you're not going to spend $10 billion on it, you're probably not going to do as good a job, so you should not directly compete with them. Does that make sense? Okay, so we talked some about processor versus streaming hardware. So now let me talk about another. If processors could do everything, you should just buy them, okay? But they can't do everything for the reasons we talked about. Sometimes don't have the right I/O, sometimes not performance enough. So, but then you could say, well, then whenever a processor is not good enough, maybe I should make a custom chip, which is called an ASIC that does exactly what I want. And sometimes that's the right choice too, okay? So let's talk about that. So a custom chip, you can just build whatever you want. Okay, so you can build any streaming hardware you want, et cetera. So it's kind of a lot like an FPGA, but it's not programmable. So, okay, so let's go FPGA versus ASIC. Okay, because that's the other decision that you're often trying to make. So you've decided that you want some dedicated hardware. Okay, a microprocessor is not efficient enough for what you're trying to do. Now you have a choice of, well, how do I get that dedicated hardware? Do I build custom hardware? Okay, so building custom hardware, this is, building an ASIC means, I'm designing everything right down to the transistor level, and I'm going to make masks that can print a custom chip, and I'm going to send those masks off to a foundry like TSMC, and they're going to build me some custom chips that do exactly what I want. I'm going to test them. I'm responsible for testing them. I'm going to make sure they're reliable. I'm going to build whatever software stack I need, and then I'm going to sell them. Okay, so I'm doing everything. So you can build custom hardware, or you could use an FPGA. Okay, so if you use an FPGA, you have to do some of that. You have to design your hardware, but at a higher level, right? You don't have to make transistors. You don't have to make masks. You just have to design your hardware and program it into an FPGA. And we'll see how that works in a while. So with an FPGA, you basically just go out and buy it. Okay, so you can buy it tomorrow. You program it, so you use the FPGA vendor CAD tools. You send, Verilog or something similar to Verilog into it and get your design in it. You test it, and you just have to test your design in it. The FPGA manufacturer's already tested that the chip works, so you know the chip works. You have to test your design works, and then you sell it. Okay, and it's not going to work at first. You're going to have lots of bugs, but you can fix your bugs relatively quickly because you could just change your design, reprogram it, try again. Okay, so your debugging cycle is somewhat like software. Okay, the CAD tools take longer, so it's not quite as good as software, but it's better than an ASIC. Okay, so that's one option. Your other option is you go to an ASIC. So an ASIC, you do your design. Okay, so you write your Verilog or your high-level language description. You make sure that you can test it. It's your problem to figure out how am I going to test this design when it comes back. You have to manufacture it. Okay, so manufacture means you actually make masks to print all of the layers on a chip. You send it off to TSMC. 6 weeks or 2 months later, they send you back a chip. You test that some more. Okay, so you did some testing in advance to try to make sure your design works. You simulated it. When it comes back, you test more. And then you sell it. Okay, so what's the advantage of an ASIC? So why would I do this? Maybe this is obvious, but we got to say it anyway. So what's the advantage? Why would I use an ASIC? What do you think? Yeah, it's smaller and faster. An FPGA is programmable, and we're going to see how that's done, but basically that programmability comes at a significant cost. Okay? So an ASIC is going to be cheaper in high volume. It's going to be basically, the die size is going to be smaller, and you can clock it faster, which means you'll get more performance from, again, the same amount of silicon. Okay? So that's good. And we'll talk some about how big that advantage is. And it's significant, right? An ASIC is actually quite a bit, depends what you're doing with it, but it's quite a bit more efficient than an FPGA. It's not a small factor. Okay, but this custom manufacturing is actually a big deal too. So it needs custom manufacturing. Okay, so you can just go buy an FPGA, but you can't just buy an ASIC. You first design it, get the masks made, wait for them to come back, etc. Okay, so what does that mean? It means your design costs are much higher. And it means it takes you longer. Okay, so you have a longer time to market. Okay, so we'll go through a couple papers in a few weeks that try to quantify how much bigger is an FPGA, but it's a large amount. I'm not going to go through all the details right now. But let's try to quickly go through, well, what does it mean? Like, that it's going to cost you more to design an ASIC. Like, how much more? How big a market do you need? Okay, so this is going to be like economics 001. It's 001 because it's hard to get precise numbers for this, so I'm just giving you my best guesses. Okay, so if you've got a big enough market, the fact that an ASIC is faster and smaller and hence cheaper means you should make an ASIC, okay? But how big does that market have to be? Okay, so there's no one answer to this. It depends on how complicated your ASIC is. It depends on what manufacturing technology you're going to use. So if you're doing a very simple ASIC in a very old manufacturing technology, then the cost of designing it is much less. On the other hand, it's probably actually slower and potentially bigger than an FPGA you would buy in a more advanced manufacturing technology. So let's just pick 22 nanometers. So not a state-of-the-art manufacturing technology, but not too old. And let's say I'm doing a complicated chip. Okay, so I'm doing a pretty complicated chip. I'm evaluating that versus buying a pretty big FPGA. And I'm probably not going to buy a 22 nanometer FPGA. I'll probably go buy like a 10 nanometer FPGA because I can. Okay? But I don't want to do 10 nanometers in the ASIC because I think it's going to be too expensive. So it's hard to give a precise number for this because it depends on how good your design team is, how complicated the design is, how lucky you are. You know, does it work first try or not? But the numbers, typical numbers that I see estimated for this, which line up with the numbers that we used when I was part of Altera. What did we think it cost us to make a new FPGA? Because an FPGA, for the people making it, it's like you're making an ASIC. You know, when you buy it, you just buy it. But if you're an FPGA company, you're actually making a custom chip. So the typical numbers that we would assume for making an ASIC was about $60 million to $100 million US design cost. Okay, so that's the cost of the first working chip. Okay, after that, the price per chip is considerably lower than an FPGA. But you know, your first FPGA cost you maybe $100 or maybe $1,000, depending on how big the chip is. Your first ASIC cost you $60 or $100 million. So, you know, where does this money come from? One cost is the masks. So you're doing custom manufacturing. At 22 nanometers, you probably need around 50 masks to print all the layers on the chip. Some of those masks are very expensive when they're doing small features. They gradually get cheaper. So because 22 nanometers is no longer like the absolute cutting edge process, it's not as expensive as it used to be. A few years ago, these would have cost $5 million a mask set. Nowadays, the masks will cost about, and again, it's hard to give like a precise number for this because it's kept pretty secret, but about $2 million US for a mask set. Okay. How many mask sets do you think you need? So you would like it to be one, but the average ASIC needs 2 complete mask sets. Okay, so it is typical. You don't get it right the first time. Okay, and you might only have to change some of the masks, but on average, you need to have 2 full mask sets. So you're going to pay that amount of money twice. That's $4 million, which is still a lot less than 60 or 100. Most of your cost is actually coming from, it is a complicated design procedure, and you do a lot of upfront verification. If you did the same kind of verification that FPGA designers do, where they just do some simulation and they program it and see if the system works, you know, you would go through 100 mask sets, right? So you can't do that. You have to do a lot more verification, be a lot more careful, and that makes your design much more expensive. This is also very visible. Like every time the chip comes back and it doesn't work, you actually have to go ask someone senior, sometimes the CEO, for more money to go get more masks. So it's like a very visible screw up. It's typical, like you shouldn't really feel bad about it because the average design team needs 2 sets. But you know, sometimes design teams need 6 sets, and that does get kind of expensive, and it does get noticed. I mean, this actually happened on some Altera chips. Like we'd be up to 6 sets of masks, and the CEO was asking uncomfortable questions about how many sets of masks are you guys going to buy, why are you screwing up so often, etc. Like it's highly visible. If you go to let's take a state-of-the-art process. So now you're going absolutely cutting edge. 7 nanometers, the estimates that I see for it are $10 million per mask set. Okay, so these numbers go up rapidly as you approach the cutting edge. But again, the mask sets are, at least for these nodes, not the dominant cost. But this is the kind of numbers you're talking about for a high complexity chip. And they are all over the map, right? So Google says that, you know, the design team for the TPU was so efficient that they're able to do it for $30 or $40 million, and maybe they could. You'll also see numbers that are significantly higher than this sometimes of how much it costs. For Altera, I know how much it costs us to design a new FPGA, and FPGAs are complicated. You have to build a lot of software around them, and there's a lot of stuff on the chip. It was significantly more than this. Okay, so our 22 nanometer FPGA family probably cost us $200 to $300 million to actually get the first chips back and working. So the numbers are pretty big. Okay, so if you're a university, you can spend all of your money on R&D, right? And teaching, okay? And teaching is important. Sorry, I forgot. If you're a company, you can't do that. So a typical model for a high-tech company is 20% of revenue on R&D. Okay, because you need to have salespeople, you need to have buildings, you actually need to pay for the chips, et cetera. You need marketing. So you can't spend all your money on R&D. Okay, why does that matter? Because it means I need to have a lot more revenue than $100 million for this to make any sense. The other thing is if you've identified a market where you think you can make several $100 million from a chip, you're probably not the only person who's identified that market. You probably have competition. So let's say that you're going to get 20% market share. Okay, so basically this 20% of revenue means I need 500 million in revenue. Okay, so I need to sell about maybe 300 million, maybe 500 million, depending on which of these numbers I take, for this to make economic sense. And if I assume that I'm not the only one who's noticed this market, I've got competition, and I take 1/5 of the market, then I now need about a $2.5 billion market. Okay, like over the chip lifetime. That doesn't have to be in 1 year, but a chip is usually only state of the art for maybe 2 to 3 years. Okay, so I need to make that money back in maybe 2, 3 years. Because after that, there's probably a new standard, probably new chips, et cetera. So there are markets this big, right? If you compare this to like, you know, the market for x86 processors or NVIDIA GPUs, they're actually quite a bit bigger than this. Possibly some AI accelerators, if it's like going to go into automobiles and it's going to go in every car. But there aren't that many markets this big. So there are some, but you basically can't identify a niche market and justify making a custom chip. Doesn't really make sense. So your choices that make economic sense are FPGA or processor. But there are some really big ones where this makes perfect sense. Okay, so that makes sense? So the other thing you have to consider is time to market. So this is just, let's say my market's big enough. You know, it's $3 billion, so it makes sense. I could make an ASIC and it would work out. Okay, so the other thing you have to consider is time to market. Okay, and I'm going to give you a completely made-up example, but it's fairly realistic. Okay, so I've got revenue on the y-axis. I've got time in years on the x-axis. Okay, so let's say I identify something new is coming out. Okay, there's a new market coming up, maybe for AI accelerators for self-driving cars. Okay, So I've identified that, and I'm going to start designing my system, my chip, and the whole system to go around it. Because sometimes, if I'm a systems company, it's not just about designing the chip. It's the chip first, but then a whole system around it. Okay, so there's some time to market. Let's say it takes me a year to get my design done. After that year, what happens is I start getting customers. Okay, so if I've made a chip, you get designed into systems. Maybe they're by your company, maybe they're by other ones, and those systems start to sell. So the market is growing for a while. And then eventually, let's say after a year after that, requirements change, a new standard comes out, competitors emerge, like the market starts to decline for all sorts of reasons, which is why you better be working on your next generation, right? You don't just ship one generation and then forget about the rest. So the market starts to mature, and let's say after another year, it's kind of gone down to zero. Okay, so there's a growing market for a while, and then there's a maturing market. Okay, so let's say I did this with an FPGA. And that meant that my cost of every chip I sold was higher. I also could have done it with an ASIC. So let's say I've got a pretty good ASIC design team. And in just another 6 months, I could have made an ASIC. Okay, so it took me a year to get the logic right. But with 6 more months, I could have figured out how to put it in an ASIC, done the custom manufacturing. Usually it takes 2 tries, so you got to wait a couple months for the first chip. It doesn't work, you wait another couple months, etc. So 6 months later for an ASIC would actually be pretty good. Your revenue doesn't start growing until this point. You start getting designed into systems. It never gets as high because you missed some of the systems have just shipped. You didn't get designed in. The market still starts maturing at the same point and goes down. Okay, so I made these figures up, okay, but for this nice triangles, this is a 62% revenue loss by being 6 months late, which sounds pretty harsh, but it's actually pretty realistic. So I mean, I lived this on some products. So so I was part of multiple generations of FPGA architectures when I was at Altera. Altera built an FPGA architecture called Stratix that did pretty well, and then Stratix 2, which did also quite well. And then we decided to do a next generation with a higher speed I/O on it. And we were going to put some clever stuff into it for power management. And that meant it took us longer than was ideal. Okay? The manufacturing process we were targeting was ready a year before our design was ready. And our main competitor was Xilinx. And Xilinx took the opposite approach. Okay? Xilinx basically did not try to change their architecture as much. We didn't think their power management was as good as ours. But they were ready when the manufacturing process in Taiwan was ready. So they actually beat us to market by 9 months to a year. And it was a terrible experience, right? It was really bad for the sales force. I'm in engineering, so it's not as bad for me as it was for them. But the sales force for a year was competing with the previous generation product against the competition's next generation. More features, newer manufacturing process, et cetera. So it was a bad experience for them because for a year they're just getting beaten up. Then we came out with our product, which was actually better in terms of specs, but the process after that came up 1 more year later. So Xilinx got all sorts of design wins. We had a better product now for 1 year. It didn't matter. I mean, it mattered a little, but basically we never made back those design wins. It was a completely terrible economic decision, and it's actually kind of inexplicable because we kind of made a plan to do this, and it was just a really stupid plan, right? Let's come up with a better architecture, but a year later, that was actually the exact wrong thing to do. It's something engineers do all the time. They want to optimize more, but it'll be better. But the year time lag was way more important than making the product somewhat better, especially because it's not the last product you're ever going to ship. There's another one coming. Well, for Xilinx, it came 2 years after their chip. For us, it came 1 year after. For that next chip, the CEO of Altera basically gave the whole every year the senior management would all get together in San Jose, and he basically gave us the #1 marching order was he said, you will not be second to the next manufacturing process. You will be first. And we were. And that worked way better. So we actually now beat Xilinx time to market by about 9 months. and the sales force was very happy, the CEO was very happy, et cetera. It was the right decision. And actually the generation after that, both CEOs said you will be first, which was actually very hard at engineering. But at least like both CEOs had kind of figured out the lesson of like you will not be second. Anyway, it's pretty interesting. I would actually often have discussions with engineers on my team who would be like, well, no, don't cut off optimization. We can make this so much better if I just have this much more time. These delays are just way worse than engineers think, or at least the majority of engineers think, more than I thought, more than the people on my team thought, more than even, frankly, the CEO thought. So it's actually a really big deal, right? It's not about getting the best product ever at some point in the future. Getting it on time is way more important than you think. And FPGAs are really good at that because there's no custom manufacturing and because you could just reprogram them to try to take out a bug, right? So that gives you this much more software-like development flow. All right, so that's kind of like why do FPGAs exist? Let me quickly go view an overview of what's inside them. Okay, and let me bring this down. While I'm bringing this down, any questions on any of that? Is it all, it's kind of my, like I said, it's economics 001 since I'm mostly making up the numbers, but it is realistic, so. Sure. Okay, good. Okay, so what's inside an FPGA? So we're going to talk about this basically, in this kind of second half or second 2/3 of the course, talk about this in great detail. But let me give you a quick overview of what's in them so they're not mysterious. And it's maybe a review for some of you. Yeah, do you have a question?
Do you have students building ASICs in academia? Is that something?
Yeah, students do build some ASICs in academia. They usually do some things, like governments subsidize it, so you don't actually have to pay the, Canada has something called the Canadian Microelectronics Corporation, the US has something called MOSIS. Academics don't have the kind of money to actually pay for all the CAD tools and for the mask costs, so it's subsidized. They also use a technique called shuttles. So you make a small chip, and instead of the mask basically printing your one chip, you have a mask that has maybe 20 people's chips on it. Now, each of them has to be small because the mask can only print a certain area, about maximum 800 square millimeters. But academic chips tend to be relatively small because they're usually proof of concepts. So they're usually not on the most advanced manufacturing process. They're subsidized by governments, and you're sharing it with like 20 other people. By doing that, you get the cost down to where academics can do it. It's still a limited number of academics because you need to have like a reasonably large group and so on usually to do it still. Like it's still a relatively, you need a fair amount of funding to do it, but those techniques keep it feasible. If you just said, and you don't pay grad students as much as you pay, this might be a secret, but you don't pay grad students as much as you pay engineers in industry and so on. So there's some other cost savings. So, and you don't worry as much about does it work perfectly. Like you make an ASIC and you start selling it to people, it better work. Every single one better work. So you've got test programs and product engineering and so on. You're a grad student who makes a chip. It's 60% works. You kind of write that down and you graduate, because that's success, right? And like you got back 10 chips and one of them 60% works, and you say graduation, right? That's not good enough for like a product. So, okay, so let's talk about the basics of an FPGA. So FPGAs are made out of, I guess at the lowest level, two things. Programmable logic, so you've got these logic elements that can do a few gates worth of logic, and programmable routing that allows you to connect things in different ways without changing the metal. Okay, so how does this work? So the most common logic element in an FPGA is a K input lookup table. So what that means is you basically program the truth table of the function into a small SRAM, And then basically you present the inputs to a multiplexer tree which selects the right bit from the truth table. That's what's shown over here on the left. Whoops. I'll get my surface going for next week. But so this can implement any function of 4 inputs. So it's a lookup table. And we'll talk about how that's built and some of the trade-offs and should you make bigger ones or smaller ones in a while. That's only enough for combinational logic, so you also have to put flip-flops in. These are just built regular flip-flops like you build in any ASIC. You might want the combinational output. You might want the registered output, so you build a multiplexer. And you build a select signal, which is just another SRAM cell, something you can program to say, do I want the combinational output or do I want the registered output? So this is basically a 1-bit wide function unit. This can compute any function of 4 inputs, and it can optionally choose to register it. OK, so that's only going to do a little bit of logic. So you typically take that logic element, and you group several of them together, often like 10 to 20 of these together, into something called a logic block. OK, so now you got something that can do 10 to 20 bits worth of logic. So it's a bit bigger, but still not that much. Most FPGAs are laid out in columns. And the reason they're laid out in columns is just to make it easier to design the chip. There's a lot of hand design that goes into an FPGA where people actually like drawing the transistors and so on. So regularity makes it easier to line everything up. So you'll normally see an FPGA built in columns. So each of these logic blocks, which had maybe 10 or 20 of those lookup tables in them, we make a few hundred of them in a column. Okay, and then we don't make one column, we make a whole bunch of them in an array. We need IOs. You can put IOs around the outside. So cheaper FPGAs usually put the IOs around the outside because you use wire bonding, which basically means gold wires that are bonded onto these with ultrasonic vibrations, and they go out to landing pads on the package that then take the signals out to the circuit board. So for a cheaper FPGA, usually the IOs are around the outside. So you can use wire bonding to connect to the IOs. For more expensive FPGAs, they're often also in columns because more expensive FPGAs use flip chip mounting, which basically means the connection to the package is made by flipping the chip upside down, and it has solder bumps all over the surface that connect into the landing pads on the package. That gives you higher speed IOs, and you can have more IOs, but it's more expensive. So cheaper cheaper FPGAs, usually IOs around the outside. More expensive ones usually have more and faster IOs, and often for them, the IOs will be in columns as well, although not always. OK, so then in between these things, you put programmable routing. So you need to be able to connect these things together to make a more interesting and big system. So you put some horizontal wires, some vertical wires. And it's programmable routing. So that means like all these things have to be programmable. So the logic elements are programmable because we basically can put in truth tables into those lookup tables to say what function they do, just program some SRAM. These programmable switches also have to be controllable by SRAM. So so in an ASIC, you just put down metal where you want to connect things. In an FPGA, you put down metal, and then you have to put down switches to connect bits of metal so that you can have the end user decide how to connect things without custom manufacturing. OK, so let's look inside the logic element for a minute. So let's say I built a really small lookup table, just a 2-input lookup table. So for a 2-input lookup table, it means that I've got a logic element that's got just 2 inputs, 1 output, and I basically build 4 SRAM cells in it, which is enough to store the truth table of any 2-input function. So let's say I wanted to build a NAND gate. So a NAND gate, A and B are my inputs here, and F is my output. My output is 1 unless both inputs are 0. So basically the way this goes into your lookup table is you have this 4-bit memory, and you would program it. Well, what would you program into it? You have a 4-bit memory, feeds into a multiplexer, and that multiplexer, the inputs to the logic element are what selects what goes through the multiplexer. OK, so in that memory, what should I program to do a NAND gate? It's like a test of whether you're following me. This is like not a hard question. So if you're going, it's too easy, no, it is that easy. So what should I put in the top bit? So the top one is what's going to come out when A and B are 0. So whatever I put in that SRAM cell, when A and B are both 0, I'm going to select I'm going to select whatever I put in that SRAM cell. So what should the top SRAM cell be? Yeah, it should be 1. What about the next SRAM? Yeah, so it should just be the truth table, right? It should be 1, 1, 1, 0. And you can see this can do anything, right? I'm just directly programming the truth table so I could do any function I want. As long as it only has 2 inputs, right? If it has 3 inputs, I have no hope of doing it. It doesn't make any sense. Okay, so that's how I made my little logic element. And 2 inputs actually turns out to not be a great choice. So we'll look at like trade-offs in how you build logic elements, but 2 inputs is simple. Okay, that only got me a little bit of logic. So now I need to combine these to make a bigger system. In an ASIC, so let's say I want to program these gates into my logic element. So I've got an OR gate, I've got an AND gate, I've got an inverter, I've got some I/O pads that I want to hook up to them, and I want to do this little circuit. So in an ASIC, you would just put down metal between the gates. You wouldn't build lookup tables. You'd build the appropriate gates out of transistors, and you put down metal where you needed it to connect the outputs of some gates to the inputs of others. We can't do that in an FPGA because we want to be able to change what's connected just by reprogramming it. So there are a few ways to do this. Again, we'll talk about it in the course more, but the most basic kind of fundamental one is use a pass transistor. So we put an SRAM cell whose output is connected to the gate of a pass transistor. If we program a 1 into that SRAM cell, it's going to connect the 2 pieces of metal. If we put a 0, it's going to disconnect them. If we put a lot of pieces of metal down and a lot of pass transistors down in a clever pattern, we can actually connect all sorts of logic element outputs to inputs, and we can realize complicated systems that have hundreds of thousands or millions of these logic elements connected. So I've shown you there one switch, right, controlled by one SRAM cell. Inside a real FPGA, there are tens to hundreds of millions of these switches. So you actually program them with maybe 100 million ones and zeros. You can't. The earliest FPGAs, people actually manually figured out what the ones and zeros were and basically put it into a programming file and then programmed it. You could never do that nowadays, right? So nobody can do that with 100 million switches. So that's where you have all these CAD tools to figure it all out for you. So you just tell it what your Verilog is, and it'll figure out how to program the chip. The dominant kind of FPGA stores the programming in SRAM, so you lose it when you turn the power off. So when you power up the FPGA, they don't actually know what to do, and it loads in its configuration from somewhere, often from a flash chip that's right beside it on the board, sometimes over PCI Express. They've got a few different options, but it's basically got to load in its programming before it knows how to do anything. Okay, does that make sense? And there's actually a little bit of tricky circuitry in an FPGA called the power on reset circuit, where when the power is being turned on to an FPGA, you have maybe 100 million of these switches in an unknown state, which actually is going to produce all sorts of power ground shorts. So you have to have a circuit in an FPGA that detects the power is turning on and basically clears all of these SRAM bits so that it disconnects all the pass transistors. If that circuit doesn't work, like it doesn't detect the power is rising, the chip will never turn on because you basically just have 100 million power ground shorts and you can never get the voltage to anything reasonable. So when actually we get new FPGAs back at Altera, that was one of the scariest things, was to see, does the power on reset work? Because if it didn't work, you couldn't do any other tests. You just had to throw away the chip and try again. And the power on reset had to work at a low voltage. Like it was difficult to simulate because if the chip was supposed to work at 1 volt, the power on reset had to figure out the power was coming on at maybe 0.4 volts and clear all the SRAM so that the chip could power up and program itself. So it's maybe more detail than you wanted, but it was interesting. Okay, so modern FPGAs have more than just logic elements and programmable routing. It turns out that if you put in some more dedicated blocks, it can be a lot more efficient. So they also have RAM blocks that store data that you can access as the end user. Pretty much all FPGAs now also have DSP blocks that do multiply, accumulate, and sometimes more. So you have thousands of these multiply, accumulate units. And those are very useful because FPGAs use a lot in signal processing. So you can do a lot of signal processing just with the lookup tables, but you can do even more if you actually put in multiply, accumulate units. Okay, so this is an actual picture of a, this is actually like a layout plot from a 40 nanometer FPGA. So a few generations old, but basically I took these pictures with me from Altera. I don't have access to the most recent ones. So the reason I'm showing this to you is just so you can get a sense of like where does the die size go. So blue in this are the logic blocks. Okay, Altera calls those adaptive logic modules, but you can see there are columns of blue, and it's probably the most common thing in the chip. So logic's probably the most important thing. RAM is in red. This particular chip has two different kinds of RAM blocks, some that have 9 kilobits, some that have 144 kilobits. They're red. It's probably the second most common kind of block. And the programmable routing is actually kind of mixed in with these. So you don't see the programmable routing, but it's there. It's just kind of interleaved right into the logic blocks and RAM blocks. DSP blocks. So this device has thousands of these multiply accumulate units, but they still don't take that much die size. So these black columns are the DSP blocks. So they take some die size, but they're not dominant. And then I said that I/O is really important. You know, people don't think enough about it. These are all programmable I/Os, all the things that I've highlighted in black. And these are kind of the more flexible but somewhat lower speed I/Os. These are used to communicate with DRAM and SRAM and a wide variety of other protocols. For high speed, basically you need a lot of clocks in these systems. So FPGAs, because they're talking to lots of things, it turns out when you look into the details of I/O protocols, you tend to produce a lot of clocks. You're speeding up and slowing down the data, you're realigning it. And you'll also have different processing elements in here that are running at different clock frequencies, things that are talking to different other chips and so on. So you have the ability to generate high-speed clocks on chip. So phase lock loops can basically multiply and divide clocks, and delay lock loops can basically shift clocks. And there's a fair amount of die size devoted to just clock generation. And then these outer blocks are high-speed serial interfaces. So these are like things like PCI Express, long-distance transceivers for optical communications, and so on. We're talking to optical transceivers that might then go through fiber optic networks. So these are really fast, right? In the latest FPGAs, these will run at maybe 56 gigabits per second or so. And so these are, you know, quite large, and to make them fast, they are a bit less programmable than the other I/Os. So that's why they're kind of special. And they take a fair amount of area. I'm not going to talk about this much. This is just basically, the only thing that's interesting here is this is going from 40 nanometers to 14 nanometers. And basically just everything goes up pretty much with the square, is exactly as you'd expect, right? So at 14 nanometers versus 40 nanometers, you'd expect that you get something like 2.5 squared more stuff, and that's basically what you get. So FPGAs tend to like advanced process nodes because they can afford it. You make an FPGA, you can sell it to lots of different people, so you can afford the non-recurring engineering charges to be on an advanced process node. And they scale well. You can just put more stuff on them. So the big advantage they get from going to a new process node is just more of everything, and there's a market for that. So Moore's Law still works pretty well. Let's see. And the last thing I'll say is, so how do we configure the FPGA? So I already mentioned this, that we have all these programming bits in the routing, in the lookup tables, also a few of them controlling the DSP blocks and so on. Most FPGAs use SRAM cells. The reason they use SRAM cells is that SRAM cells are very standard. Every process node can make SRAM cells, and FPGAs want to use advanced processes. So that's the fundamental reason that they like to use SRAM, is you can now use a regular process. There are a few FPGAs that use flash cells. They're nice in a way, because they actually remember their state, and they can be smaller. But they have a disadvantage if they require a custom process. Which means they're usually not on the latest and greatest process node. So when you turn the FPGA on, it loads in this bit stream so that it actually can start your computation. And I'm not going to show this in detail, but the basic way it loads it in is the FPGA, all that SRAM in an FPGA kind of behaves like a regular SRAM. You basically, the programming hardware reads in a row of the configuration, and then it essentially writes it to one row of this SRAM that's distributed through an FPGA. And it'll repeat that maybe 10,000 times to write all of the rows in the FPGA, so all of the 100 million bits. And now your FPGA knows what it's doing, and it knows it's configured, and it will start operating. The thing that is important about that is that it means that to change the FPGA bit stream, what it does, takes a lot longer than in a processor. In a processor, it has an instruction that's maybe 32 bits wide that says, what am I doing this cycle? In an FPGA, the equivalent instruction is like 100 million bits long. It's like encoding all of these lookup tables and these routing switches and so on. So it takes a lot longer. It takes like 100 milliseconds or so to load that in, which means that FPGAs, it's a lot harder to change what they do. It's possible, but in a processor, you can kind of change what it's doing in a clock cycle. In an FPGA, to change what it's doing, it takes you, millions of clock cycles. It takes like 100 milliseconds or so, which means people don't do it as much. It's possible, but they don't do it nearly as much. And so that's it. I will post next week's reading, which is basically just a kind of relatively high-level overview of FPGA architecture from the optional textbook for this course. So this reconfigurable computing book we'll do a few readings from. It's in the library. You don't have to buy it. So before the lecture next week, you have the opportunity to submit the questionnaire for this. And remember, you want to do that for at least 10 of these through the course. So I'll put that on Quarkus, and it'll be some of the background for next week. Okay, thanks, everybody.